Hey guys, these are your notes on elevators. Write down everything I write down, and even some things I say if it helps you out. Write down some things I say if it helps you understand it better. Okay. Um, so here I have a picture of an elevator, and we have somebody standing on a scale in the elevator. And throughout these notes, we're going to focus on the person and not the elevator box itself. What's happening to the forces on that person. All right. So what forces, say this is the elevator, it's at rest right now. What forces are acting on that person before, the elevator jumps? Well, they're on Earth, so there's the force of gravity on them. And they're also not falling through the floor of the elevator, so there's a support force called the normal force applied to them, and those should be equal lengths as they are balanced when the elevator is at rest. So let's just prove that why they're balanced, okay, when the elevator is at rest. So when the elevator is at rest, there's no acceleration up or down. There's no AY. That's 0 meters per second squared, right? So if you were to apply Newton's second law in the y direction, our net force would be the up force minus the down force. And AY would be 0 because you're at rest, not moving up or down. So then what would happen to Fn and Fg? Well, this whole m times 0 is 0. And if you add Fg to both sides, you get that Fn equals Fg, and that means that they are balanced. So whatever your weight is when the elevator is at rest, the scale reads the same thing. The floor needs to support you with the same amount of force when you're at rest, because there's no acceleration in the y direction. Alright, so, and we've looked at Fn, it's measured by the scale. And the scale actually tells you how heavy you feel. When you were pushed down into the scale, there was more normal force. So what it tells you is your apparent weight. Fn tells you your apparent weight, or how heavy you feel. Alright? And we all know Fg, that's our real or actual weight. But there's some times where, you could feel weightless, you could feel a little heavier on an elevator, and you could feel a little lighter, and that's what we're going to look into next. And when those things happen, what is changing is what the reading on the scale is changing. And that tells us our apparent weight, or how heavy we feel. It's the normal force, how hard the floor pushes on us. If it pushes harder on us, there's more normal force, and we feel heavier. We have a higher apparent weight. If the floor pushes lighter on us, then we feel lighter, and we have a lower apparent weight. But that doesn't change how heavy our real weight is. Okay, so let's look at 3 situations. We're going to look at, we were at rest on the elevator before, right? Now we're going to accelerate up. Then we'll just kind of move at a constant speed. So we're going to the top floor. We bumped up, accelerated up, and we continue to move at a constant speed. And our last situation will be when we arrive at that top floor and you slow down, or in that case you will accelerate down. So we went through all the parts of a elevator ride in this video. We're going to do, at rest, speed up, move at a steady speed, and then slow down. Okay, so when you accelerate up, you have a positive AY. Alright? Now, based on Newton's second law, applied in the y direction, if I have an AY that's positive there, my mass is always positive, so I will end up with a positive net force also. Positive AY, positive net force. So that means when I look at FG and Fn, the net result of those needs to be a positive number. So when I accelerate up, Fn needs to win to get me to speed up upwards. Fn needs to be greater than Fg. And I like to draw it like this too. See how Fn is greater than Fg right there when we accelerate up. Fn needs to win. So what does the scale read when we accelerate up? Scale reads a greater apparent weight. And what do you feel? When the scale reads a greater apparent weight, you feel heavier. So the normal force, remember, that dictates our apparent weight and how heavy we feel. And it's measured by the scale, right? When normal force is greater than gravity, the scale is going to read a greater apparent weight, and we're going to feel heavier. And think about it, doesn't the floor push on you a little harder to get you to accelerate up at the beginning of that elevator ride? You feel that jump, and you feel the Fn be a little greater than it was before when you're at rest. But after you get up to speed, you don't feel heavier for the whole ride. So you start moving at a steady pace with no acceleration for most of the ride, actually. And we know, based on Newton's second law, when AY is 0, our net force is also going to be equal to 0. So that means when our net force is 0, there's no leftover between Fg and Fn. So in that case, nobody's greater. They're balanced, Fn and Fg. So most of the ride, your apparent weight at the scale reads is equal to your real weight. So scale reads and apparent weight equal, that's Fn, your apparent weight, and that's equal to your real weight. Because you're not speeding up or down, so they're balanced. What do you feel? You feel normal for most of the ride, right? You feel heavier at the beginning, bump, and Fn is greater, and the scale reads a greater number. And then that's over. You kind of feel your normal weight, whatever Fg is, that you feel the force from Fn equal to that. Okay, so now let's get up to the top floor, okay? So you got to slow down when you get up to that top floor. You kind of have a negative acceleration when you slow down, right? So in order to have a negative acceleration, it's not that your Fn totally disappears, it just doesn't win. The floor is still supporting you a little bit, but Fg has to win to get a negative acceleration. And we could show that with Newton's second law that if you have a negative AY, you're going to end up with a negative net force right there. A negative net force means Fg needs to be greater. Let's keep writing Fn on the other side. This time Fg needs to be greater than Fn, right? And what do you feel in this situation where Fn shrinks to kind of allow you to slow down and get that negative acceleration? What is the scale reads? Scale's always reading Fn, so it reads a smaller apparent weight. And for a moment, you feel this light feeling in your stomach, like everything's detaching, you know? The scale reads a smaller apparent weight. That is Fn. And how do you feel? You feel almost weightless. Or at least lighter. Almost weightless or lighter, right? And why do you feel lighter? Because to get to slow down, we'll let gravity do the slow down, and we don't need an Fn to balance it out if we want to just slow down a bit. So the scale doesn't really need to push up if you don't want to travel up anymore and you want to kind of slow down. And for a moment, the scale doesn't read anything, or it reads, maybe 10 pounds, and that's it. So you feel lighter.